Hello everyone and welcome to We Meet at Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is filter components, mode of operation and selection criteria. Our speaker is Mario Möller. He will hold a presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the question window. You will find the question window in the control panel. This presentation will be about 30 minutes long and the chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just email us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the presentation, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out a survey and help us to improve our event. You'll receive the link for the presentation in the next few days, and the recording will be available at our website shortly. So now I will hand over to Mario, to our speaker, and I wish you an exciting presentation.
So, hello everyone. Welcome to today's session about the basics regarding inductive filter components. We're going to talk about their mode of operation and selection criteria. This presentation is set up like an FAQ of previous technical webinars that we've held before. We've collected most frequently asked questions and some feedback on what you wanted to learn about regarding our inductive filter components, and this is what we got. My name is Mario Möller, Field Application Engineer at Würth Elektronik, and I'm specialized in passive components and EMC. Today we're going to talk about the physics, so what is happening inside the inductive filter components to make them behave like they do. In the next step, for the selection criteria, we'll talk about the different noise transmission modes and respective filter choices. Of course, every filter has its limitations regarding bandwidth, so that's another subject for this session. Especially for inductors, saturation is also an issue to be taken care of, making it another criteria for your component selection. Last thing is the difference between impedance and attenuation, because this is sometimes a source of confusion regarding the selection of filter components. So let's go straight in. For the inductive filter components, we should first talk about the definition. What is a ferrite? What is an inductor? A ferrite is, strictly speaking, a form of iron oxide, or a somewhat special form of rust, if you want so. It has a high permeability, which increases the inductance for those components where it's used as a core material. So it's not only used by itself in a ferrite ring, as we can see here, but also as a core material for a wide range of different types of inductors. What is an inductor? An inductor is technically a wire that is wound around, some kind of magnetic core, and can be either used as a short-term energy storage or as a filter component, as we will see today. Depending on the construction, different properties for this inductor can be achieved. For example, a rod core choke, as we can see here, will behave differently from a high current power inductor that we will use in a switching regulator. But what are the constructive elements that make up that behavior of the inductor? Well, first we're going to talk about the core material. Besides the ferrite material, we can use iron powder or some special alloys as a core or shielding material for the inductor. This will influence the actual inductance of the inductor and also the impedance, but also the saturation behavior and the frequency response. The same applies to the shielding ring because the same materials are used here. But when we're talking about the shielding, it's mainly about the actual construction of the inductor. A shielded inductor will have less of a stray field around it than an unshielded inductor. However, more ferrite material means less of an air gap, and so the saturation sets in a lot earlier. Next, we take a look at the wire. Here we have a round wire on the picture, and this is what most people come to mind when thinking about an inductor, because well, the round wire is easiest to manufacture. However, there are different types of wire that can be used, like, for example, a flat wire for high current filter components, or for an SMD ferrite, we don't use an actual wire at all. For an SMD ferrite, there's actually a rather thinly printed in a silk print process, a rather thin layer forming the winding of the coil. The wire drives DC losses and therefore the self-heating of the inductor, and therefore limits the component's current capabilities. So the thicker the wire, the more current it can carry, of course. Inductors can, of course, be placed on the PCB using THT or SMD mounting. But at this point, please don't forget that also a snap-on ferrite or a solid ring ferrite placed on the cable is an inductor. So these have to be put in mind as well. While mechanical considerations for the forces keeping the inductor on the PCB are important, the placement of the inductor regarding the source or the sink of the noise also has an impact on its performance as a filter, as we will see later. The electrical characterization for an inductor, in this case an SMD ferrite, as you can see here in the middle, can only be done from the outside. We consider the component a black box. Using different measurement equipment like a VNA or an impedance analyzer, we can determine the properties of the component. For two-port measurements, as we can see here, one input, one output. However, there's not much that we can observe here, but the voltage and the current going through the component to calculate the impedance, to characterize all the electrical properties of the component. So let's take a look at the impedance curve over the frequency range. This measurement is done at our headquarters in Waldenburg using an impedance analyzer and gives us this beautiful curve. Looking at this curve, we'll have a pretty standard choice for an SMD ferrite, a 600 megahertz, 600 ohms in SMD ferrite, and these 600 ohms are a rated impedance at 100 megahertz. So this is pretty much this point. Regarding the curve, at the first third of the curve, we have pretty much what we expect from an inductor. We have a pretty straight line, increasing impedance with frequency. But this straight line does seem to take a little notch and does seem to bend at maybe 20, 30 megahertz. So what is happening in this first third of the curve? The impedance in this part stems from the basic inductance of the part. The inductance can be calculated from the geometry, the number of windings, and also from the relative permeability of the core. Here's an example for a toroidal choke, because this was the most obvious formula that I could find. But even for an SMD ferrite, the formula is pretty similar, so you get the gist of what is happening. The inductance increases with the size of the inductor, because, well, the area of the magnetic field does play a role here, and with a number of turns around the core. Turning up the frequency will then lead to a higher impedance, as you can read from this basic formula. Calculating from a point on this curve, we can determine the actual inductance in this SMD ferrite. And using this formula, we get about 2 microhenry for this small SMD ferrite. But as you can see, there's a lot of impedance curves. There's a lot of the impedance curve still not really explained. So what is happening in the 2/3 that we haven't looked at yet? The first thing that we see is that the impedance curves takes a drop after the self-resonance frequency. And this drop is explained by the parasitic capacitance inside the ferrite. Every real component will have some parasitic elements that cannot be avoided. In every inductor, there will be some kind of interwinding capacitance, so a capacitance between the different windings. However, for an SMD ferrite, this interwinding capacitance is shorted, and the capacitance between the actual winding and the SMD terminal of the component is dominant here. So this is what makes the bandwidth limitations for an inductor, and in this case for an SMD ferrite. We can change or switch up the layer stack inside the ferrite a little bit, as we can see here. This is the layer stack of a CBF HF, so for RF frequencies. Here we have turned the layer stack 90 degrees, increasing the number of capacitors that are switched in series, and switching capacitors in series will decrease their overall capacitance. So we will have a lower capacitance and therefore a higher self-resonance frequency. So using just, some little neat tricks and switching up the construction inside the ferrite will lead to different impedance curves. Each of these 3 ferrites will have the same rated impedance in the data sheet. So they all have 600 ohms at 100 megahertz. But as you can see, their behavior in the application will be different. So we have the wideband curve, which is useful for filtering of switch mode power supplies, for example. But then there's also the high speed ferrite, which can be used if the only differentiating factor between the noise and the useful signal is frequency. So if we have no mode differences, then we can use this high speed ferrite to filter our high frequency noise while not affecting the useful signal. So this is what's going on in the 3rd part of this curve. We'll have this parasitic capacitance. Also, again, we can look at this curve and calculate the capacitance, which will be about 0.7 picofarads, at least for this SMD ferrite. But then again, what is happening in the middle here? So normally we would, for a power inductor, for example, we would expect some resonance points, so a sharp edge in the middle of the impedance curve. But this is not happening for this SMD ferrite. So what is happening here? The SMD ferrite also has a DC resistance, which will dampen this resonance point. However, looking at the actual material-specific resistance of copper or silver in this case, there's no way that we will get this much of an resistance in the middle of the curve. So taking a look at the data sheet, we see that the DC resistance stemming from the actual winding only makes up about 0.45 ohms, which is not a lot. So this doesn't really explain the capping of the impedance at this point. So something else must happen here. So what is happening here? To be honest, there is a little magic going on inside the coil. Because when we're looking at this formula, XL is omega times L. This is just considering the air coil part impedance of the whole inductor. As soon as we're introducing a ferrite core or any magnetic core to the inductor, we will have to multiply L0, so the basic inductance of this air coil with the relative permeability of the core. So the reactance of the inductor will be greatly influenced by this relative permeability. I want to spare you the boring maths here, but just to get you the physical understanding of what is happening here. Permeability is pretty much the ability of a core material to draw in the field lines of the magnetic field. It's also a measurement for how much energy do you need to magnetize the material or to demagnetize the material. This actual magnetization of the core is measured in this B field, and the relation between the B field and the H field is, well, this is considered this mu. However, between the B field and the H field, there can be some phase shift, and this phase shift then has to be somehow represented in this material constant, which is mu. And because this phase shift is also frequency dependent, mu, or this relative permeability, is not really a constant, but rather a function of the frequency, as you can see here. So we have this mu1 and mu2, and mu2 is, considering this frequency shift, a complex term, meaning we have an imaginary part of the permeability. So multiplying this into our formula that we've had before, and we'll now get JXL, so the reactive part of the impedance, but we also get a resistance. So we have an actual frequency-dependent resistance that is stemming from the core losses that are introduced by this ferrite core inside the inductor. Here we have two different curves for the magnetizing permeability. So for the one that is that makes our XL, and as you can see, for the low frequencies, this XL or the mu1 will be dominant. So for low frequencies, it's easy to put energy into the inductor and get all of the energy out. However, with a rising frequency, we'll have more of a phase shift between the magnetization of the core and the actual B field inside the core. So this will result in losses inside the core, and also some self-heating of the core. So this will highly be dependent on the core material used inside the inductor. So for example, if we would take an iron powder core, we will have losses in the rather low frequency range, about a megahertz. And if we're taking a look at the manganese zinc or nickel zinc, which is used in power inductors, for example, we will have these losses in a much higher frequency range. So we can use nickel zinc cores in power inductors at a megahertz or even at 10 megahertz without having a lot of core losses for our switch mode power supply. However, we can use a manganese zinc core for conducted emissions, because manganese zinc will draw a lot of core losses in this frequency range up to 30 megahertz. So depending on the application, we can switch up the core material to achieve different properties here. Going back to our ferrite that we've looked at before, we can see here the not only the impedance of the SMD ferrite, but the impedance analyzer will also give the phase of the impedance or the angle of the impedance, and therefore we can deduce the actual resistance part in this inductor, yeah, and this impedance of the inductor. So the gray dotted line here is the actual resistance depending on the frequency. For SMD ferrites or for any inductive filter, we of course want to use the frequencies. We want to use that working point where most of the energy is really burned inside the core or is used up inside the core as losses. So this is where we want to be at. This is the sweet spot for SMD ferrites or any inductive filter component. We want to be as close to the self-resonance frequency as possible if we want to filter. Of course, we can go a little below the self-resonancy point. We can go a little above the self-resonance point. However, we don't want to go far above the self-resonance point because at this point the part will act as a capacitor and not will have the desired behavior. Yeah. Okay, so these are now the three components that we have here for this SMD ferrite. Just looking at the impedance curve, we have about 2 microhenries of inductance, 0.7 picofarad of capacitance, and 750 ohms of frequency-dependent resistance. I've just looked into the LT spice parameters because sometimes you might want to simulate this component. And this is what we have for this component in the LT spice model. This is just straight from the library. This is not prettified or something. This is just straight from the library. So we have an R parallel of 752 ohms, which is pretty close to what we have here. We have a parallel capacitance of 0.67 picofarad, which is also pretty close. And then we have an inductance of 1.8 microhenry. There's about a 10% difference, but you have to know that SMD ferrites are manufactured with 10 to 20% of tolerance. So this is well within the tolerance band of manufacturing. This is a pretty good measurement, I think. Okay, so this black box does not is not just transmitting energy from point A to point B, but there's also some absorption of energy, which is then given to, well, the air around the SMD ferrite, but is also given to the PCB below the ferrite. So again, the actual mechanical construction of the PCB and of the housing of the PCB will have some influence on how much current this SMD ferrite will be able to carry without getting too hot. Yeah, so this will happen to a differential mode signal going through the SMD ferrite. So we will have some kind of attenuation here. But also keep in mind that beside this transmission and absorption of the energy, we will also have at least some kind of reflection at both edges of the part. So we have some impedance mismatch between the actual signal line and the SMD ferrite. So there will be at least some part of reflection of the signal here. And this part of the reflection might, might affect signal integrity if we have really only this means of filtering. And especially for unbalanced transmission, these low paths of first order are really our only way to filter. If an unbalanced or common mode signal is introduced here, it will have a rather great impact on the load. Because the voltage across the load cannot be distinguished between the useful signal and the noise signal. The only thing different, the only thing differentiating the useful signal and the noise signal at the load here will be the frequency. So for unbalanced transmission, we can only use line filters like an SMD ferrite, or like maybe we can even use a rod core choke or something, depending on the frequency and the current that we want to filter here. For balanced transmissions, we have a little more options. So when using an idly balanced transmission, a common mode noise signal has no impact on the load. But of course, we know that no signal is that no system is perfect, and there will always be at least some disbalances between the two paths here. So we will still have to use some filters. However, using such differential lines, it's easier to filter our noise because now there's another differentiating factor between the useful signal and the noise signal, and this is the direction of the current or the transmission mode. There are two typical noise transmission modes, the first one being the differential mode, which will use the same paths as our useful signal. The differential mode noise is, for example, the ripple current, which is modulated onto the output of your switch mode power supply. And then we have the much more sneaky common mode signals, or the common mode noise. The common mode noise will use both lines in the same direction and will use the earth or protected earth as a return path. So the common mode noise will use ways that we might not really anticipate. However, we can use this different way of using the lines or these different directions of the current to our advantage. For example, we have broadly saying, a USB driver here. And this USB driver, we are having at least some noise on our square signal. We have a little hair here. And let's see what's going to happen if we put some SMD ferrites or any normal line filter here. And what we can see is that the noise is really reduced, but also we're cutting off the edges of our rectangular signal here. So this is not what we want to happen. So instead, we're going to use a common mode choke. A common mode choke will have the current going through the first line, the same current going through the second line. And by using our right-hand rule, we can determine that the resulting magnetic fields in the core will compensate each other. So there's no magnetization of the core for the useful differential mode signal. However, for the common mode signal, there will be resulting magnetic field inside the core, meaning that we will have actual magnetization or core losses inside the common mode choke. So we will have actual attenuation of the common mode signal without affecting signal integrity. So what's happening here is that the differential mode signal can go into the choke and go back through the common mode choke without much happening. But for the common mode signal, there will be some core losses, reducing the common mode effect on our application. Or in the ideal case, we will have no common mode at all in here. So for our signal, this would mean that the high frequency noise is cut off, but the signal edges or signal integrity is not affected. Of course, this is only the case for ideal systems, and we don't have an ideal system here. Real common mode chokes will have at least a little bit of influence on the useful signal. So the stray inductance will have a differential mode impedance, and the stray inductance, however, is much smaller than the common mode inductance. And being much smaller, this means that also the impedance is much smaller and is only effective in much higher frequency ranges. So we can protect a useful signal in the lower frequency range from common mode signal without really dampening the signal. At least this is what we want to do. Yeah, so going back to our black box system, even for the even for the differential mode signal, we will have at least some attenuation of the differential mode signal and some impact on our signal integrity. We can do some constructional tricks to the common mode choke to reduce this influence of the stray capacitance. And this is the B-filar winding in contrast to the sectional winding. The B-filar winding will have a much lower stray inductance and therefore will affect the useful signal or the differential mode signal much less. The sectional winding will have a rather high stray capacitor, will have a rather high stray inductance and will therefore reduce differential mode signals in the high frequencies. But this can be used to our advantage, just considering, for example, common mode chokes for mains lines, because there is no useful signal in the high frequencies that we have to protect. Speaking of common mode common mode for mains lines, we also have different ways of constructing these common mode chokes. For example, comparing a common mode choke with a ring core or with a toroidal core versus one with a frame core, we will see that the frame core has a much lower interwinding capacitance because we have these separate chambers where the windings live. However, because we take more space for the windings, we can only use a little smaller a little smaller wire. So the current capabilities of the frame core will be a little less than the toroidal core. In this example, we have the CMB with the same inductance as the FC series that we have here. And as you can see, the FC series will have a much higher self-resonance frequency than the CMB. So the inductance or the impedance curve seems to be a little better here. However, we can only carry about half the current of the toroidal choke. Again, I have to remind you that some slides ago that the attenuation is not only happening by absorption, but also by reflection at the edges of the component. So this is not only happening for the common mode, So the common mode, of course, is reflected, but also a little bit of the differential mode is reflected. And also a little bit of the differential mode signal is converted to common mode, and a little bit of the common mode signal is inverted to differential mode. So we have this mode conversion inside the common mode choke, which for a lot of cases is not really that important. But if you attended the talk from my colleague Martin Leienseder yesterday, this might be important especially for long data lines where a mode conversion from common mode to differential mode and from differential mode to common mode is really an issue when trying to comply with the standard. All these different behaviors like the transmission and the absorption and also the reflection of the differential mode and the common mode signal can be characterized by looking at the scattering parameters. These scattering parameters are measured using a 4-port measurement on a vector network analyzer. And to put it easily, we will introduce a certain amount of power to one port, which we can see here, and then we measure each port for how much power will come back for a certain frequency range. So all other ports are measured for amplitude and their phase shift of the signal. And with a little bit of calculation in the background, we can then determine the transmission, reflection, and absorption of the common mode and the differential mode, and also the mode conversion. So how much of the common mode signal will be converted to a differential mode signal, really affecting our useful signal. and how much of the differential mode signal will be converted to a common mode signal, which will then lead to radiated transmissions. Also, these scattering parameters or S parameters are the basis for all of our impedance graphs in the data sheets. If you want to learn more about these scattering parameters, again, we have a lot of information on using these in a simulation. And for most components, you can find the S parameters for free and without registration on our homepage. For example, for the SMD ferrite that we had earlier, you can find, or for a common choke, you can find the S parameters on the respective product page. Running a little bit out of time here. Let's go straight to the saturation effects. For an air choke, we will have almost no saturation effects because, or we will have no saturation effects because you cannot saturate air. For a magnetic material like ferrite, however, we will have some saturation. If we introduce a magnetic field, there will be some influence on the molecular magnets inside the material, and they will all try to change their direction to accommodate this external magnetic field. But at some point, all these different molecular magnets will have the same direction. So there will be no little magnets to turn. And this is a status that we will call saturation. And in this saturation point, there is no inductance left because, well, you can't further magnetize the core. Of course, these saturation curves or these BH curves will again look different for all the different core materials that we have. Here we have the nickel zinc and manganese zinc, but we also have a very special core material which is called nanocrystalline. And as you can see, you have a very high or steep curve in this in the beginning of the curve, meaning that we have very high permeability. So we can achieve inductors with or common mode chokes with a very, very high impedance. But also you can see that the saturation point will set in very, very early. So you will get an inductor with a very high inductance and a very high impedance, but this inductor will also saturate very quickly. So it is only suitable for very small signals, as we will see later. This is also the case for a power inductor, of course. Many people use a power inductor as a filter, for example, in the input stage of a switch mode power supply. And for switch mode power supply, you can see, especially in the input filter stage, of course, you can use an inductor with a shield ring. Yeah? However, using an inductor with a shielding will have a much earlier saturation due to there being less of an air gap. For the input stage of a switch mode power supply, you can also use an unshielded inductor because they will have much more saturation reserves. So a higher current will not rob them of their inductance, of their impedance. And because we don't have the high DI to DT or the high jumps like we have at the switch node, we don't have to expect that much of a stray field for the input filter in a switch mode power supply. So for the input of a switch mode power supply, a ferrite choke, an unshielded ferrite choke is a pretty good choice. For an SMD ferrite, we also have a saturation behavior. And as you can imagine, we have only very, very little of the ferrite material here. And this very little material can be saturated very fast. So introducing a current to this SMD ferrite will result in a drastically different impedance curve. This DC bias behavior, that's its name, can also be simulated using Red Expert. So if you're interested in how does this SMD ferrite work in my application with the actual current that I'm using, I highly recommend to use Red Expert. Okay, now we have talked about power inductors, and we have talked about SMD ferrites as a filter and how they are saturated. But in the next step, we're going to look at the common mode choke. And surprisingly, when we take a look at the data sheet of a common mode choke, we can see no saturation currents. This could mean two things: either that the choke is never saturated, or has a very, very large saturation current that is not plausible to achieve with this choke or with a wire, or that the choke can be saturated very fast, so it doesn't make sense to include any current here. And the truth is that it's both. For a differential mode signal, we can see that we will have almost no magnetization of the core, meaning that with the differential mode signal, it's almost impossible to saturate the core of a common mode choke. And this makes the saturation for the differential mode, well, not really necessary to put it in the data sheet, because the common mode choke will most likely soldering itself out of the PCB before it gets saturated. However, for the common mode signal, we have to consider that we are magnetizing the core, and we have no air gap in this system. So we can saturate the core pretty quickly, as we can hear for the common mode chokes for data lines. For the SL2, for example, that we have here, we have a starting inductance of about 250 microhenry. But introducing only 100 milliamps of common mode signal will lead to a drop to about 6 to 7 microhenries for this SL2. So even a very small common mode signal will lead to a very quick roll-off of the inductance for a common mode choke. Of course, for the common mode chokes for mains lines, it's not very different. You can see this very steep behavior in the inductance roll-off, again for the nanocrystalline core material. So the nanocrystalline core material might have a very high inductance, but it's also very quick to drop if introduced to very high common mode noise. But this is also something that we have to learn here. Common mode noise in most cases does not exceed more than some microamps or a few milliamps. So if you have common mode signals in this or in this range, there's totally different problems going on with your application. So you shouldn't really bother with the saturation of a common mode choke, because for this differential mode signal, it's implausible, and for the common mode signal, it will happen too fast to make anything about it or to do anything about it if you really have that much of a common mode signal. Then we have also the cable ferrites. Cable ferrites are again sensitive to the transmission mode of the current going through. Again, for the common mode configuration, so we have the current and the return path. You will have almost no saturation of the core, or let's say the saturation is at least in edge case, because you will have not the same balance between the two lines as you have with a common mode choke. There will always be some mechanical differences between the two lines, so you don't have this balanced transmission here. So it also can saturate in common mode. To fight this behavior, we have introduced the Star Gap series, which is a snap-on ferrite with a defined air gap. And this defined air gap will lead to a higher saturation current for this cable ferrite. For the differential mode configuration, as we see on the right-hand side, there is really a risk of saturation. So while this will work as a filter for the differential mode, if you just put one wire through the ferrite core, the ferrite core again will saturate very quickly. So this is well, not the intended use case. Okay, last thing, system impedance. When you look for a filter, it's important not to go for the highest impedance, but rather check the ratio of the filter impedance to your system impedance. Because the insertion loss or the attenuation is pretty much dependent on this ratio, as you can see here from the formula. You can calculate the minimum filter impedance using this formula or using the nomogram as we have in the catalog, or you can use Red Expert to calculate the actual minimum filter impedance. However, to get the ratio of this filter impedance to the system impedance, we will need to know the system impedance. And because this is very hard to measure, we have at least some values that we found from experience, and that is for a power supply we have a system impedance of 10 ohm, and for clock or data lines we have an impedance 50 ohms and up. So using these empirical values, you can calculate the needed filter impedance to get to your desired attenuation in the system, either using this formula or using this nomogram that we have here, which is pretty much just this formula drawn out to a diagram using different system impedances for the source and the sink. The last thing to consider when choosing an inductive filter component is well, the actual impedance curve. So at what frequency do I need the impedance? This is another indicator if you should use a power inductor or a normal SMD ferrite. But this is also the case for common mode chokes. So please don't just look for the rated impedance at the top of the data sheet, because depending on the frequency of your noise, a smaller common mode choke with a lower impedance but a higher self-resonance frequency will have much better attenuation in your application than expected. Also, if an inductive filter is not enough, you can always use a filter capacitor to decrease the system impedance and therefore have a higher attenuation just by using not a low pass filter of first order, but of second order. And well, this is it for today, I guess. Do we have any questions?
Yes, thank you, Mario, for your interesting presentation. I have to say, really sorry for this, but we are running out of time, so we've got no time for the questions now. So I think we will just summarize them and then we can answer them afterwards via email. I'm sorry for this.
Okay. Sorry.
So no problem. So yes, just one more hint from my side. We will start with the next presentation at 3 p.m. and the topic is magical micro modules with adaptive switching, all-in-one solution for the industrial sector. From Timo Ulodak, he will present this and hopefully see you there. Thank you, Mario, for your presentation and everybody for being here, and have a good day.
Have a nice day. Bye.
Bye.